Hi, everybody. We are back, and in this segment, we are going to be discussing classification problems, and we're going to start off by taking a look at logistic regression as a tool to implement in solving classification problems. The agenda today is going to involve the following. We're going to start off by looking at how to use a linear regression to achieve the task of classifying qualitative data. Then we're going to see logistic regressions really more appropriate for doing this, especially if you want to think about the idea of estimating probabilities or likelihoods. And then in the next segments, we will talk about how to actually estimate it using an iterative method, gradient descent, which we had introduced earlier, and comparing the linear regression framework to the logistic regression framework and another variation known as a linear probability model. So we're going to take care of the two blue arrows in this first segment here. So let's start off talking about linear regression. If we were given some vector of input data x, so this is our x0, x1, x2, x3, x4, or our input data, and we have our beta vector, right? Beta 0, beta 1, beta 2, beta 3 out to beta k, if we have k plus 1 independent variables. Then the way we could think about writing out the summed products of our x's and our betas, right? Beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. What we're actually doing when we compute that is we're calculating something called the signal associated with the regression equation. And for the linear regression framework, the signal was literally the entire right-hand side of the equation, right? Beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth. And note in this notation here, we have capital K independent variables here, and we're starting the index at 0, which means we have really k plus 1 betas to estimate, k plus 1 parameters to estimate here. And the linear regression model, what that did is we were really trying to predict the expected value of y conditional on the features x. So we were taking over here what is known as a conditional expectation. Right? What is the conditional value of y given these individual x features? We use the term h of x to think about our hypothesis structure, right? About that conditional function that's capturing this conditional probability. And in terms of this idea of a signal that we just introduced here, okay, we can really think about that regression equation as just being a linear function of that signal s. So this function theta is something new we're going to talk about today. That is called a transformation function. And in the linear regression case, the output that we were dealing with was a scalar variable. Okay, there was an infinite set of possible values, potentially maybe censored in some sort of range there, but it was a continuous output variable. And the transformation function theta here was linear. It was just the signal. There was no other nonlinear function we ran the signal through in order to calculate y. We just added up beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth. And that allowed us to compute fitted values. Now, you could do classification with a linear regression. And we'll talk about that in just a moment. But the general structure of the linear regression hypothesis looked like the following, right? Our hypothesis, our y value as a function of x, was just equal to that signal. And again, the signal was beta 0 times x0, which is 1 for regression, plus beta 1 x1 plus beta 2 x2, so on and so forth. So the way we can kind of visually think about the regression model here is we were taking all these inputs, right? We took all this x data, these input variables here. We plugged them in to our signal, and then that signal, okay, determines for us the optimal hypothesis, right? The best prediction given those x values. And I want you to note that we're using a linear threshold function here. Okay, that's why there's like a straight line in that bubble. It's a linear function. It's a straight line that converts that signal into the hypothesis on the right. Okay, so this is just a visual representation of linear regression model when we have a continuous output, right? You can fall anywhere on that linear line. If we wanted to use linear regression for classification, you could do this. It's not a great tool, but it is possible. Okay, given again the signal here in red, we could define some threshold value. Let's call it S bar, some constant, where if we plug in our data and the signal is above that constant, we would classify that data, that data point is one particular class. But if the signal isn't high enough, it doesn't breach that threshold, then we would not classify it accordingly. So for a linear classification problem, using this linear regression tool here, we can predict a binary class of output given the signal. And the way we would do that is given this user specified threshold S bar. Hey, what we can do is we can compute the signal S, right? Take the betas, multiply them by the X's, add them all up, compute that signal, and we check if the signal is greater or smaller than the threshold. So we're looking here, so take a little bit of explaining, at the sign of theta of S and S bar, and if theta is the linear function, it's just whatever we plug in there. And then what we're doing here is we're looking at the difference between S, the value of the signal, and S bar, some threshold. If S is above S bar, then you get a positive value, so we would assign the +1 class. They're in that group. But if S is below S bar, then we assign a value of -1. So it's literally the sign here of S minus S bar that would determine if we classified something in one category or another. And if you want, of course, we can recode those outcomes from -1, +1 to 0, 1. It either happened or it didn't. It was in that class or it was not in that class. And again, in this situation, we're still using a linear transformation function. What do I mean by that? Well, that transformation function here was this function, S minus S bar. S is linear. It's not squared. There's no log or anything like that. So still a linear transformation function. And you may have seen this idea of using linear regression for classification in this way when we do things like look at risk scoring or credit scoring. Okay, consider computing your risk for cardiovascular disease, right? We know there's a number of factors that affect cardiovascular disease, your risks like your blood pressure, your cholesterol, whether or not you're a smoker. And we can estimate with a fair amount of precision here, at least some, given a large amount of data, a risk score. Okay, we can compute a linear risk score here by running this linear regression. And the idea would be the following. If your risk score is high enough, right, if it's above some threshold, and that threshold the doctors would have to define what is a sufficiently high risk score to put you in a high risk category, they would diagnose you as high risk. And if you were below that threshold, then they would diagnose you as low risk. So that threshold here would be S bar. That is a user specified threshold. And setting S bar high or low is going to affect the sensitivity of the binary classifier. If that S bar is really, really high, okay, then it's going to look like you don't have a lot of people with cardiovascular risk. You miss out on diagnosing people that do have it, but you set the threshold a little bit too high. So we have to think about that, right? Setting that threshold is going to affect the rate of false positives and false negatives, and that's actually an issue that we're going to have when we apply logistic regression to classification, is that when we estimate the probability of something happening, we're going to have to think about, well, what is a reasonable threshold probability to use, potentially in certain cases. So we'll come back to that. Now, again, with the linear regression applied to classification, the hypothesis here, right, depended on X, it depended on the signal, but we argued, given that threshold, we could just look at the sign of the signal. And the output from this was not continuous. So I'm going to be very clear about that. When we're looking at the picture here, the output from this was either +1 or -1. It was binary, 0 or 1. You were either in the class or you were not. You were in the high risk category for heart disease or you were not. Okay, so this threshold function here in the bubble, it looks like it's really sharp. It goes from 0 up to 1. It jumps, right, real quickly. And this is kind of an extreme case. What we're going to wind up doing with logistic regression is we're going to look at a softer threshold function that allows for values not just 0 or 1, but potentially in between, depending on the strength or size of that signal. Okay, so let's go ahead and talk about the main topic today, which is logistic regression. So again, given our signal here, a logistic regression is used to compute a continuous probability. Okay, so you might think, oh, I thought we were dealing with binary classification. Well, we are, but it's going to give us a continuous probability, and we're going to interpret that probability to predict a class or not. If I say I get a probability, it's 99% chance that it's in class A, then I'm going to predict it's in class A with 1, right? It's not in class A, 0. Now, the form of the logistic regression function is a little ugly here. We're going to take some time interpreting it, but it looks like this. The very left-hand side of this function, this is our y variable, and it's not y, it's the probability of observing y. Okay, however you've defined what y is. And for a binary outcome, it's either y or not y. So we're looking at the probability y occurs given x, and the form of our hypothesis function uses a non-linear transformation function. Okay, the signal now goes through this really ugly function that depends on exponentials in the numerator and the denominator. So our regression equation looks really ugly. You have exponents with the beta showing up, you have fractions with the beta showing up in the denominator. So this is a highly nonlinear problem here. Okay, and that means, well, one implication of this rather is that when we go to calculate the optimal parameters to fit this model, there's not a nice, beautiful one-step analytical solution like there was in the linear regression framework. Now, the output here, it is a scalar. It is some number between 0 and 1. It's some probability measure. And the transformation function, again, is this theta of s function. It's e to the signal divided by 1 plus e to the signal. And you can show with a little bit of algebra, you can rewrite it this way, but we'll also write it this way. It's convenient too. So again, that transformation function, that's kind of the tricky part for us to negotiate here, right? And the transformation function, this is something we refer to as a sigmoid function. It's like an S-shaped function. And what this does is it implements what we call a soft threshold, okay, when we apply this logistic transformation. So the logistic transformation takes what was a linear signal S, and it produces for us a non-linear output, okay, which is this whole term circled in blue. That is a non-linear function of the signal, which is why this is a non-linear regression. Now, what's the idea? Well, this threshold function is between 0 and 1, so it has a very nice probability interpretation. When the signal gets very high, okay, it pushes the probability up towards 1 asymptotically, can't exceed 1. When the signal gets very low in the negative direction, that pushes the value of logistic regression's output here towards 0 asymptotically. Okay, the likelihood it's not happening. Okay, if you get a 0 prediction, probability is 0, then it's predicting it did not happen. So all we're doing here is we're using this soft threshold function to transform that signal, which could have been between negative infinity to infinity, to a restricted domain that has values restricted between the interval 1 and 0. So we can interpret these as probability measures. Okay, now the form of the hypothesis here is not just the signal, right? It's the theta of the signal. It's the transform of the signal. So the diagrammatic interpretation of the logistic regression function is going to be a little bit different than the linear regression function. We don't have a straight line threshold here, right? It's not a straight line threshold, and it's not a rigid threshold. It's not 1 or 0. Okay, but it's giving us some continuous probability between 0 and 1. So we refer to this situation here, okay, as a function that is utilizing a soft threshold to transform the signal. right? And as we mentioned before, there is a probability interpretation, right? Our hypothesis, h of x in logistic regression, is interpreted as the probability of observing y, okay, given x. So in our earlier example, we were talking about predicting heart attacks, right? The input, the x data is like your cholesterol level, your age, your weight, whether or not you're a smoker. Theta of S would be, instead of your risk score of getting a heart attack, it would now be interpreted as the probability of you getting a heart attack. So again, your risk score of getting a heart attack, that is the input here. Okay, but the output, theta itself, is the probability of a heart attack. Okay, but the signal, again, is that linear component. The signal is linear, but the theta function is nonlinear. So when we plug the signal into that theta function, that is why this is a nonlinear regression technique. Okay. Now, the data we know, right, is generated from some underlying data generating process, some function f. And the way we're going to be thinking about this is the logistic regression is going to be measuring the probability we observe y given x. Okay, so our data generating process is some function that either determines y has happened or y has not happened. Y happens with probability f of x, or y happens with y does not occur with probability 1 minus f of x. So the target function we're assuming here, that data generating process, that target that we're trying to estimate, we're assuming that is some function that maps to the unit interval. There's some probability function in nature, and we're going to try to model that. Okay, the idea being here, we want to learn, the best hypothesis in order to approximate the actual data generating process F. Here is our optimal hypothesis, and in logistical regression form, it is going to be a transformation of that linear signal, a nonlinear transformation of that linear signal. So I want to wrap up this segment by just kind of doing a little bit of algebra with the logistic regression equation here. We just saw that if you can think about the dependent variable now, the y variable, as being the probability of an observation belonging to a class, so that 1 minus y is the probability the observation does not belong to the class, then the highly nonlinear logistic regression equation looks like this, and it's not pretty, right? Not pretty. We saw it before, but we had the signal plugged in now. We substituted in our beta 0 plus beta 1 x1 plus beta 2 x2, so on and so forth for the signal. And the question is, in this nonlinear form, how do we interpret the betas? They're not slopes anymore because our regression surface isn't a line. It is a hyperdimensional manifold. It's like a three-dimensional surface that's curvy, or a hyperdimensional surface rather, that is nonlinear. And the way we're going to interpret the beta coefficients here is going to require us to just rewrite the linear regression equation a little bit. So we're going to do a little bit of algebra here. So regression equation was this. And we're going to go ahead and plug in the signal, okay, S, in order to rewrite this thing in a little bit more compact form. So this thing and this thing are the same. All we did is we plugged in S for the signal here and here. And we're going to just manipulate the compact version of this. When we need the betas to come back, we can resubstitute them back in through the signal S. So let's go ahead and start with the bottom line. Let's move that up to the top on the next slide here. So the logistic regression equation we kind of wrote like the following. Okay, and we're going to rearrange this expression. Let's go ahead and multiply through by the denominator. So we'll move that 1 plus E, we'll move that over to the left-hand side. Now it shows up here. Okay, and then we're going to go ahead and take our Y term and we're going to distribute that in to both. So we get Y plus Y e to the S on the left. And my goal here, by the way, is I'm going to solve for S. I'm going to get S, the signal alone, so we can see really how to interpret the betas. So let's go ahead and add the y e to the S term back over to the right. Let's move that over. And we can factor out an e to the s on the right-hand side now. That leaves us with the 1 minus y times e to the s. And then I'm going to divide through by 1 minus y. And you'll notice we almost have s by itself, but we have that number e, that's the natural number, 2.7 something. And you might remember, hopefully you remember from your algebra class or maybe your calc class, the inverse function of that is the natural log function. So if we take the natural log of both sides, okay, the natural log of e to the s is just s. Okay, and what we are able to do now is we've showed that these two equations are the same. That equation and this equation down here, the one circled in green, these are actually the same equation, right? And it turns out the bottom one is a little bit easier to think about when it comes to interpreting the beta coefficients. So let's go ahead and discuss that before we wrap up this segment. So we have shown that these two equations are identically describing the logistical regression. Okay, the left-hand side of the expression on the right, okay, so that is this side here, that term is known as the log of the odds ratio. Okay, log of the odds ratio, which means y over 1 minus y, that is the odds ratio. That's the probability of it happening divided by the probability of it not. Okay, if you have a coin toss, right, that's 50% divided by 50% gives you 1-to-1 odds, right? It's your odds ratio there. But it's the log of the odds ratio. That is what we have here. So if we look at the entire expression now, plugging in for our signal, we get back all these betas over here. And we can now interpret the beta coefficients. Okay, so if you have a 1 unit increase, let's say in x1, what beta 1 tells me is how much the entire left-hand side is going to go up. That's what beta 1 is going to tell me. A 1 unit increase in x1 translates to some unit increase in the left-hand side there. Well, what is the left-hand side? That left-hand side is the log of the odds ratio. It is the log of the odds ratio. That is what we're measuring on the left-hand side there. So the way we're going to interpret the beta coefficients here, a little bit different than in linear regression. Beta I, for I bigger than 0, meaning not for the intercept term here, measures the increase in the log odds ratio. It's a likelihood ratio, but it's called the log odds ratio, resulting from a 1 unit increase in the variable xi. Okay, so the interpretation of the betas are a lot different in logistic regression. Okay, it's telling me how the log of the odds ratio goes up. Okay, by how many units does it go up when we increase the x variable by 1, holding everything else fixed? Okay, if beta is negative, then that means you get a decrease in the odds ratio. That means that x variable makes it less likely to observe something in the particular class that defines y. Let's go ahead and think about maybe backing up one step and working on some interpretation here. So if we back up one step, let's raise both sides to the base e. Okay, so I'm going to have a base e on both sides. And again, we mentioned earlier that e and the natural log function, they are inverses of one another. So when I take e to the natural log, okay, what are we going to be left with? We're going to be just left with this y over 1 minus y term on the inside there. Okay, and now on the right side, we have e to the signal, right? That whole term in the blue box, that is our signal s. And we can actually break this up. If you remember, if you have exponents added together, that happens because you had values with the same base being multiplied together. So we can rewrite that right-hand side as the product of a bunch of exponential terms, right? E to the b0 times e to the b1x1 times e to the b2x2. That is the same thing as this expression up here. What do you do when you multiply numbers with the same base? You add the exponents together. And this allows us here to see a little bit more clearly that this value, e to the b, here, e to the b0, e to the b1, what that measures here, it's really a multiplicative factor that affects the odds ratio itself. And you could interpret this, and this is more true for the non-intercept terms, but you could think of e to the bi. If you were to get the regression output from running the logistic regression model, you got your betas, and then you take the number e as the base to the beta power. That number will give you 1 plus the percentage change in the odds ratio. So if your e to the beta power value, if e to the beta is like 1.2, what that means is holding the other factors fixed and increasing that x variable will increase the odds ratio by 20%. So if e to the beta was 1.2, again, that means if you increase x by 1, that increases the odds ratio by 20%, by 1 plus the percent change in the odds ratio. Again, and this is from a 1 unit increase in x holding other factors fixed. Okay, so if you get your betas and you raise them to the base e, take them to the base e, so you have e to the power of that beta. If that number is bigger than 1, that's telling you that that factor is increasing the odds ratio. Okay, that factor x has a positive relationship with the probability you're estimating. If e to the beta is smaller than 1, okay, then it's reducing the odds ratio. So again, we started with this form of logistic regression equation up here. Okay, we showed that e to the beta can be interpreted as 1 plus the odds ratio. So if e to the beta is greater than 1, then xi has a positive effect on the odds ratio. It multiplicatively increases by this factor e to the beta I. If xi has a negative effect, then e to the beta I will be between 0 and 1. And if e to the beta I is equal to 1, then this really corresponds to x having no effect on the probability of observing y, or on that odds ratio. So a little bit tricky here, thinking about how to interpret those betas and how to use them for prediction, but not impossible. Okay, we just have to use this exponential function and use that as the base and raise it to the power of the beta that we're interested in, and thinking about the multiplicative effect a factor has on the odds ratio, on the relative likelihood of the event occurring. So that wraps up this segment. We will pick up momentarily looking at how to construct the likelihood function and implement gradient descent to solve the maximum likelihood problem here. And then we'll wrap up by talking about a couple of variations of gradient descent and the linear probability model. See you soon.